Projectile motion. What is a projectile? Well, that's a projectile. And if you thought that was a myth, there's a photograph. That's a human cannonball. It's not an actual, gunpowder gun, cannon thing, because it would rip the person to shreds. It's a ram or a big spring, I don't know. But while he is flying through the air, he is a projectile. That means that the major force acting on the object is weight caused by gravity. Obviously, on Earth there'll be some air resistance, but what there is not is any significant propulsion or lift. Airplanes have propulsion and lift. Gliders have lift. Rockets have propulsion. Falling leaves have significant air resistance. None of these are projectiles. The only thing that's a projectile is something whose major force is weight. Mathematically, let's look at this example, this half example. Here we have a horizontally projected ball. It's already at some height. It's kicking it from a ledge or something. What happens to it? Well, it follows this particular path known as a parabola. Why? Because you have to treat the horizontal and the vertical components of its velocity completely separately. Why? Because as we said, the only force is weight. Now, we haven't really studied, if you're watching this for the first time, we haven't really studied the effects of force. But as a sneak preview, overall force causes acceleration. If you have a force in the direction of the motion, well, put it another way. If you have an overall force, you'll have acceleration in that direction. Since the force is at right angles to the velocity, there is no acceleration acting to affect that velocity. So the velocity is unchanged horizontally. Nothing's speeding it up, nothing's slowing it down. So ux, the initial horizontal velocity, is the same as vx. The final horizontal velocity makes no difference. On the other hand, vertically, there is a big difference because there is a force acting vertically. It may start off, in this case, with 0 vertical velocity, but over time, since there is a force acting in that direction, then that will grow. And those two motions added together, the constant horizontal velocity and the increasing negative vertical velocity, create this parabolic curve. Since we have two lots of constant acceleration, vertically 9.81 meters per second squared, horizontally 0, constant velocity, but still constant, we can use the Suvat equations. They are available for us to use. And it is using those equations that we analyze the motion of a projectile. Horizontal is pretty simple. As I've said, displacement equals velocity times time. The velocity, the x, ux, the horizontal component of velocity is constant, so we just multiply by time. Well, how do we find time? Well, we can look at that in a minute, because there we have to look at the vertical velocity. S equals ut plus half at squared. Again, just another equation of constant acceleration. V squared equals u squared plus 2as. And we can use these equations, simplified by the fact that in this case, u is uy. The vertical velocity starts off as 0. Now, I'm not expecting you to remember these equations. These are the equations that we turn them into. We're not expecting you to remember these equations or these equations. No equations here will be remembered. Instead, I expect you to be able to remember that you have to use the equations of constant acceleration and how you can use them. By substituting in, by getting rid of the u because it's 0, and by substituting in the acceleration g instead of a and sy instead of s because we're just talking about the vertical, etc., etc. Here's another couple of equations. Here's how we adapt them. Okay. Let's look at an example of their use. Suppose we want to find a range of a ball that's kicked with a horizontal velocity of 10 meters per second from a height of 10 meters, and we'll assume, to make life simpler, acceleration equals 10 meters per second squared. We take one of our previously mentioned equations. Alright, we want to know the range, but in order to find the range, as we said earlier, we have to find the time. Okay, so we have to find time. So we take this equation that we already have looked at. We plug in our numbers, try and find t. Work it all out, t equals the square root of 2 in seconds. So the range equals the horizontal velocity multiplied by time. Horizontal velocity is 10, therefore the range Sx equals 10 root 2 meters, so about 14 and a bit meters. The more general case of projectile motion, it starts off on the ground, ends back up on the ground. Now we haven't really looked at energy yet, not own forces, we haven't looked at energy, but by conservation of energy, the kinetic energy it starts off with goes to potential energy, goes back to the same amount of kinetic energy, ignoring air resistance, and therefore the speed it starts off with is the same speed it ends up with. All that's different is the direction, same velocity. So again, we can split this into vertical and horizontal components. Here's a reminder, the vertical is v sine theta and the horizontal is v cos theta. Horizontal is pretty much the same as before, the horizontal component, v cos theta, multiplied by the time. And vertical, well, this is s equals ut plus a half at squared. We can't ignore u, because now there is an initial velocity in both directions. Now, despite what it says here, we'll make acceleration negative, because this is positive, so s equals v sine theta t minus a half gt squared. This equals ut plus, but now minus because it's down, a half gt squared. For a complete flight, sy equals 0. The displacement from the start to the end is actually 0 in the vertical plane, not in the horizontal plane, but it is vertically. Therefore, we can substitute that in. 0 equals v sine theta t minus half gt squared, minus half gt squared equals v sine theta t. Divide by t, rearrange, and you get t, the time taken for a projectile motion, equals 2v, the initial velocity, sine theta, the angle to the ground, divided by g, the acceleration due to gravity. To find the height, that's half a motion, so time is a half t. Plug that into v squared equals u squared minus 2as, or a version of it, and you end up with this equation down at the bottom. Again, I'm not expecting you to remember these equations. I am expecting you to remember that you have to use the equations of constant acceleration and that you have to manipulate them. Of course, those equations only describe the situation in situations of no air resistance. If you do have air resistance, then I think the effects are fairly predictable. It won't go as high because of the drag vertically, and it won't go as far because of the drag horizontally. The actual effect, how big of an effect you get with air resistance, depends on the properties of your projectile. Is it streamlined? Is it not streamlined? Is it heavy? Is it light? How affected is it by the air resistance? There is a Colorado simulation of this, which is really good. If we turn off air resistance, then it doesn't matter if we're firing a tank shell, or if we're firing a bowling ball, or if we're firing a person. Go human cannibal, and bang. Or if we're firing a Buick. They all follow the same path. But once we introduce air resistance to the equation, then it does have a varying effect. Tank shells, very little effect. Tank shells are aerodynamic, they're heavy, very little effect. A bowling ball, bit bigger, definitely an effect. A pumpkin, big and relatively light, a very big effect. Oh, and I hit the target. Yay! Result. And let's try the piano. Quite big, quite heavy, and it goes splat. So different air resistance there does have an effect depending on the mass and the aerodynamic properties of the material. Okay, thank you very much.